Hi everyone. Up to now, we have considered only the NMOSFET, where electrons are mobile carriers. Of course, in reality, we have the PMOSFET. In this lecture, the PMOSFET simulation is sketched. First, the bias condition is discussed. For the NMOSFET, the source is typically connected to the ground. Then the gate to source voltage VGS and the drain to source voltage VDS vary from 0 to VDD. And the drain current has a non-negative value. On the other hand, for PMOSFET, the source is typically connected to VDD. Also, VGS and VDS vary from minus VDD to 0 volt. The drain current has a negative value. So, when we draw the IV characteristics of the NMOSFET and the PMOSFET together, they are found in the first and third quadrants. Yes, it is natural, but second and fourth quadrants are empty. In many cases, in order to deliver information in a more compact way, the absolute drain current is used as the y-axis variable. Now, let's simulate the IV characteristics. Especially, we will find that the work function is important. The PMOSFET has the opposite doping polarity against the NMOSFET. The substrate is N-type doped and source and drain regions are P-type doped. In this example, we just use the same absolute value with the NMOSFET. Only the sign of each doping profile is inverted. Without changing the work function, our 50 nanometer long PMOSFET shows these IV characteristics. Two curves are corresponding to the drain voltages of 0.05 volt and 1.2 volt. Once again, it is noted that the IV curve occupies the third quadrant of the plane. The drain current level is very low even at the on current condition. In the absolute value, the threshold voltage seems to be too high. Roughly speaking, it is about minus 1 volt. Well, we want to have a value near minus 0.4 volt. When we take the absolute value of x and y-axis variables, we can compare the PMOSFET result with the NMOSFET ones. It is clearly seen that the PMOSFET with a work function of 4.3 electron volt has too high absolute threshold voltage. After measuring the difference between blue and red curves, 0.7 volt difference is found. The right way is to increase the work function. Instead of 4.3 electron volt, the work function is now 5.0 electron volt. And the drain current is greatly increased in its absolute value. When the same comparison made again, the black curves corresponding to new P-MOSFET result are well matched. The P-MOSFET curves are shifted exactly by 0.7 volt. Yes, the work function simply shifts the IV curve. Interestingly enough, although the subthreshold behavior is quite similar, the on current is much different between two MOSFETs. In the case of N MOSFET, the red curve, the on current is about 1.2 milliamp per micrometer. However, in the case of the P MOSFET, the black curve, the on current is just 0.8 milliamp per micrometer. Since holes have lower mobility, the P MOSFET has a lower on current. In order to check the carrier mobility, the absolute gate to source voltage is set as VDD. Then carrier mobility is drawn along the vertical direction. Of course, the cut line is made at the channel center. The electron mobility of N MOSFET is much higher than the hole mobility of P MOSFET. Therefore, we have different current levels. In order to have a similar ion level, the width of P MOSFET should be larger than that of N MOSFET. We will revisit this issue in the next lecture. Okay, that's it for this lecture 14. In the next lecture, we will consider a CMOS inverter. Thank you and see you later.